All right, good morning. It is Monday, 23rd of March. We're entering week 2 of our pause from in-person instruction. Just me here today and one out of focus loaf up there. I think Nuno is chilling. That's good. Today also I'm wearing something. It's a free T-shirt I got from a company that published one of my academic posters I gave at a conference. I only kept it because it's comfortable, but it says experiment, fail, learn, repeat. So I don't know, all of this video making and online instruction is a bit of an experiment. So we'll see how it goes. The slides I want to talk through today are about color mixing, some very interesting stuff. A lot of people coming to this class know a little bit about it, but the more I studied it, the more counterintuitive parts of it felt. I remember my first interactions with colors being things like, red and yellow make orange, blue and red make purple, kind of thing. But there are a couple of different ways to combine colors together, and there are some fun online resources that let us experiment a little bit. Not meant to be that long of a class. Everything that I link to in my slides, I also have linked to on Canvas as well. But yeah, it's not meant to be that long because normally when I run this unit, we're also doing like the measurement part, the big part 2 of a lab. So I've filmed a lot of that, so you can participate in that at your convenience at home. But yeah, this part isn't that long, and often I'll go through and watch some of the YouTube videos, and instead of spending the time on that here, I've linked to them all on Canvas, whether it's articles, YouTube videos, or whatever. So I think I have slides ready to talk through, and pages going. So just to show you one thing that's a little bit out of date, we have. Right. There's my web window there. This is normally week 9 content. I'm going to adjust these PowerPoint slides because I've added a couple of things. The main thing is this interactive light and color applet link. The homework I assigned this time is not terribly long, and it gives you some places where you can explore that a bit yourself. I've always asked my classes to do it. It's just as convenient to have you do it too. Then everything I recommend as far as watching and reading, all here. I'm going to post this video here as well too when it's done. The main thing I'm going to be looking at are the light and color simulations. So we can look at the entire electromagnetic spectrum if we want. I'm definitely going to be looking at color addition, maybe a little bit of painting. I don't know about colored shadows or filters. You can explore a little on the homework. It's some of the same principle, and stage lighting as well. Those are my 3 favorites that I've gone through in the class. Also, just as a fun preview, this Interactives has something called Young's experiment on it. It's not for this week, but I'll let you know what it's about. I haven't seen exactly what this, I know what the experiment is, but I know what this is supposed to look like. We can make this look bigger. The idea is if you take a laser and you shine it at 2 slits, you don't get 2 bright spots, but you get a pattern of bright spots that's here. Actually, this looks pretty nice. I could, remember that we saw this here. It might help with some of the questions. This is one of the labs that we're going to do later, and I've already filmed it and taken pictures and everything, so you can take and analyze the same data that we would have had we done the experiment. This one lets you switch between different lasers. Oh yeah, so right, you can see if you change it from red to green to blue how the pattern changes. That's a topic for another class. I just got excited to see this here. It is something we'll be doing later. So all right, these are the simulations that we're going to be looking at, and let me stop my share there and then go to slides. So here they are as I have them. There's 18 total, and they're not too terribly long. I always start by pointing out there are different forms of color addition here, additive and subtractive. So additive is like what happens when you add different light colors. Subtractive is when you're absorbing things and combining absorbers, sort of a way of looking at it. Right. Some of the simulations I have show this stuff off in greater detail. We have little boxes in the lab room that let us do this too, but this is one of those cases where the simulator does just as good of a job, I think. So we're going to be doing color addition, color subtraction. If you're familiar at all with web design or web coding, you've heard of, or even just design of anything. I mean, even in Microsoft products, you can customize colors by putting in hex codes, like everything from 000000 to FFFFFF. Any combination of numbers from 0 to 9, letters A through F, you can put in that code. It gives you a different color addition. That's using the RGB, right? Red, green, blue. When we talk about color addition, red, green, and blue are going to be our primary colors, and then I'll talk about the subtractions a little bit later. This agenda is basically thrown out of the window. I do plan on the 2-lens lab being something that you take at least 2 weeks of time to do. You won't be choosing the separation between lenses yourself because, right, I had to just pick one to let you all take data. All right. My last talking through slides. We did microscopes and telescopes a little bit. I think it talked about Hubble and the James Webb, which is coming up next. And microscopes also have an eyepiece and an objective lens. Also, we didn't talk about it in great detail, but I spent some time doing a 2-lens example in a separate video. If this were our normal class, we'd do the math part of the lab I handed to you even before we parted ways. We played with equipment a little bit, and all of this lab stuff is meant to take 2 weeks. So this is the lecture portion of week 2. I've linked all of this through Canvas already. The physics classroom is a good place for all of this, and I've linked to specific simulators there, but I've already prepared those in my window to go. Okay, so you can get the links from the slides, or I've put this key one on Canvas, and you should explore that if you want to check this stuff out more on your own. And I mean, I'm not going to get fully into these different terms. We are going to be talking mostly about wavelength and mixtures of wavelengths. So that relates the most to hue. So that refers to the main color or color name. Are we talking about a red or a blue or something else? Now, saturation, not a term I quiz about a lot, but there are more than one way to get yellow. You could have like a laser light focused around one specific frequency and wavelength, and that gives you yellow, or you can get it by mixing other colors together so your frequency set is sort of smeared out. I'll show you what graphs of that look like a little bit later. And brightness and lightness are other factors which, you know, if you're looking around a color wheel or looking to describe a color that you're seeing, those are other adjectives that we might use for, right, intensity or how much grayness or whiteness. Should be with an E. Ooh. All right. So, right, those are overarching terms. We're going to mostly talk about the first two. And a review of wavelengths is that visible light has wavelengths between 400 nanometers and 700 nanometers. So violet has the shortest wavelength and also the largest frequency. And red light has the longest wavelength and the smallest frequency. Because remember from before we broke up in person, frequency times wavelength is the speed of the wave, and all lights go roughly the same speed. So if your wavelength is nearly doubled, your frequency is nearly cut in half. Still probably sharing the PowerPoint slides, right? I think so. Let me just show off one other idea. Going to Chrome, go back here. It's not really I guess this is supposed to be an interactive, but I'm showing off the very first link on the electromagnetic spectrum, which we haven't seen the whole thing that much. Let's see if this shows. Oh, interesting. It's not even loading at all. See, this is what I get when I try to be spontaneous, but these kind of technical glitches happen all the time when I'm doing this live. So I like to think of this, I'm providing you some of the authentic experience. All right. I was hoping to show off something that looks kind of like this, right? The electromagnetic spectrum here. Those wavelengths of 400 to 700 nanometers occur in this very tiny visible spectrum here. So 400 to 700 nanometers are all less than 10 to the minus 6 meters. And so very small region. You can see there are much larger regions for radio, microwaves, infrared, ultraviolet, and the X-rays and so on, right? So very small range in frequencies and wavelengths for the visible colors. And those are the ones that we're going to be mixing. So back to the agenda. We used to recommend a really old textbook. It's been out of print for a while, but I've stolen some diagrams from it. We can depict light or the mix of it with an intensity distribution curve. This helps us understand things like saturation too. So basically we map out all the wavelengths that are possible, that are visible, and say how much intensity do we have at each one. That's a way of getting the picture correct. So the intensity distribution curve is in this bottom here, and on the x-axis, in case you can't see it, we have 400 to 700, and those are the wavelengths of light that are possible. We're thinking purple on the left, red on the right. And this one, since it has a big peak, in the 500 to 550 nanometer range, this would look green to us. If you were around and got to see the green lasers that we have, the wavelength for those is around that center. So, right, your big peak is here. This is going to tell you a lot about the main hue you see. Now, you can mix in a little bit of red. That'll give you a different color and a different intensity distribution curve. So this book just wanted to add a little extra red. So if you do that, you kick up the right side of it a lot. They wouldn't look the same, but they would both look predominantly green. Now, some other mixing that goes on would look something like this, and we see some different saturations as well. The primary colors for addition are blue, green, and red, and they're on the top. So your blues are going to be less than 500 nanometers, green is going to be in the mid 500s, and red's going to be above 600. I think 650 is the standard wavelength for the red lasers that we use in class. So we have those too. And what explains what goes on when you mix them is you just mix the intensity curves and see what the overlap is like. Now, for me, it was a very strange thing, like what happens when you get green and red. But if you take the green curve and the red curve and you just simply add them up, you can just take the results from the two curves and you combine them, you get a new curve with a new center around it. And the thing you see when you mix those two colors of light, green and red, is you get this middle one labeled with Y. That's going to be yellow, so I'll show that off in a second. So you get green and red, you add them, you get yellow, blue and green, you add them, you get what's called cyan, and magenta and red. Blue and red, add to get magenta. So magenta is a color that you get that has kind of this, looks like a Bactrian camel or something, a two humped sort of thing. And since blue and red are more separate from each other on the spectrum, right? It's not like you get a clear peak in the center. So it's not like you can add these two together and get something in the middle, but it does result in a color called magenta. If you mix all three colors, you get a flat frequency spectrum. We'll see what that looks like in a second. And pictures G and H show two different ways of getting yellow. If you take just monochromatic yellow, you get a very sort of pure color there. But if you were to mix something that's pure green and pure red, you can get yellow a different way. You can perceive it as yellow, even though there's no peak around the 600 spot where normally we would expect it to go. All right, so I'm going to next go, well, two things. One, I'll show you in Chrome here. All right, I do link to a video which shows some interesting international perspectives. Different languages, different peoples see colors differently, and I'm not gonna show you the whole thing, but right, in some cultures they would consider these two just shades of the same color, even though we would separate them into blue and green. There's also a linguistic bit that dark blue and light blue sometimes get different color names. He shows off some Russian and Greek, and like, so to us, like this lighter blue in the bottom is what we would call cyan, but the word for dark blue in some other languages is a word that's very, very close to cyan. My limited knowledge of how to read Greek letters and Cyrillic letters tells you that, and he shows it off in this video. So a lot of the way we perceive colors is a bit culturally dependent, but what we can agree on is, you know, at least what they look like through color addition here. So let me make this a little bit bigger. I encourage you all to do the same kind of thing, right? You have red, green, and blue, and I have them turned up all the way. If you combine the red and the green, you clearly see a yellow mixing there. And this is called color addition, additive mixing, we would say, right? So add these two and you get yellow. Green and blue together give you cyan. So this is what we call cyan, this light blue sort of thing. And blue and red make magenta. It's not what like 6-year-old Tim thought of as purple, but you get magenta. And then you can make the Venn diagram. You combine all three of them and you get a white region in the center, right? So right, red, blue, green, we can see the intersection. Green plus blue makes cyan, red plus blue makes magenta, red plus green makes yellow, and then the sum of all three colors makes white there. So white is what you get in this bottom picture if you basically have a frequency chart or an intensity spectrum that includes all the visible wavelengths. You're going to get something that looks like white. We're going to see that later when I talk about stars a bit. So, right, this is an image on the slides in case any of this doesn't work for you personally. You can always refer to this as adding light, and a summary of adding the primaries together is the three additive primaries are red, green, and blue, called RGB. Right, RBG is a Supreme Court justice, so I'm going to label them RGB when they're colors. Right, so R plus G is Y, R plus B is M, and B plus G is C. We can get those colors that way. Now, another thing that happens is sometimes color subtraction. You get mixes of absorbers, really. So really, when you're looking at a colored object or a black object, you don't think of it as they're giving off their own light. They're probably reflecting some other light from a light source in the room. So behind me, right, there's a black cat tree with a black cat on it. I'm wearing kind of a gray shirt myself. Okay. It's not like there's something emitting something black or even really gray there. Really, what has to be going on is some kind of color absorption, right? Oftentimes, like to make colors on stage, you use colored filters. So what those do is they absorb certain colors and let certain things through. when you look at objects like a black object, right, they could receive any color in the spectrum and absorb it. So if they don't reflect anything, it doesn't get back to you. So combining filters or combining pigments even means you combine the things that get absorbed, not the light that's put out. So, right, the color of an object results when an object subtracts certain colors from white light. If you look at like a red t-shirt, that means the red t-shirt is reflecting red and absorbing green and blue, right? Or if a piece of clothing is yellow, that means it is reflecting some combination of red and green and absorbing everything blue. If we're talking about like the RBG primary colors. So the colors that were in these intersections here, yellow, magenta, and cyan, they're called the subtractive primaries when you think about colors. So again, going to a picture from the very, very old textbook. If I can make this even bigger, maybe a little bit. Okay, so these pictures, they're not intensity curves, they're transmittance curves. So we can think about filters this way, right? A blue filter, this is this first picture, lets through all the blue, 100% transmittance, and filters out everything else. An ideal green filter lets everything in the middle through and filters out everything else. An ideal red filter lets none of the blue through green through and lets the red through. So those are the filters. If you combine any two of these filters, nothing can get through, right? Like combine the first two, right? If you combine blue and green, if it's not blocked by this first filter, it will be blocked by the second one. So any combination of two of these three, if they're ideal filters, will leave you with nothing getting through. It's effectively black, right? But we have filters we can combine. See, how do these go? They're labeled in the slides, so download them if you can't see them right. This picture here called E is a yellow filter. We're filtering the blue out, but letting the red and green through. This one, we're filtering the green out and letting the blue and red through. This would be a magenta filter. And the cyan filter lets the blue and green through, and not the red. Right. So we can also think of these subtractive primaries as like white light minus one of the primary colors. And we can do a subtractive mixing rule here. Now the book was done in black and white. It's not terribly interesting, but we can see it in color here. So subtractive combinations look something like this. The subtractive primaries are magenta, cyan, and yellow. You can think of yellow as either green plus red, or it's called a subtractive primary because we're subtracting just one color from white. If you take the blue light from white, you get yellow. If you take the green light from white, you get magenta. If you take the red light from white, you get cyan. And so the thinking here is if we use these as like subtractors, we can get any color we want as well as black. Just like I would use RGB for adding colors, the abbreviation for the subtractive primaries is CMYK. So K is black because B is taken for blue already. So right, K like this. And there are different kinds as well. You can get black ink by combining yellow, cyan, and magenta. This is like an annoying thing I've heard about with color printers. You can't print black because you're out of magenta ink or something like this. Some printers have separate cartridges just for black, and there are different combinations of it. We started talking a little bit about Vanta Black and things that are, extra absorbent in class, but I don't need to dwell on that right here. It was as of February 3rd of 2020, so about a month and a half before I'm recording this, our new printing studio in the Wabash building got set up. And I took this picture from the front window. one of the big um, one of the big printers in there, you could see the color cartridges right from the street. So this was through a window, and it was very, very clear YCM. The letter K is right there. So these are giant ink cartridges. It says what each one of them is: yellow, cyan, magenta, black, right? And these go basically in one of the giant machines in our printing studio. So this is something that was right on campus, and so fine. In my slides, I mentioned that you can see the Tom Scott video. I've linked to it on Canvas. And I'll finish up by just mentioning a few other things. Rods and cones. We're going to talk more about the eye later, but rods and cones are photoreceptors in the eye. So rods see black and white and are good at dim light. You don't see color as well in the dark, and you don't need to. We just needed to have something that perceived changes in light level in case something was hunting us. When we were evolving as a species, you have a lot of these, and the cones are responsible for color vision. Those are centered around the fovea in your retina. More on that a little bit later. But you should know that we have three kinds of cone types. They're either called short, medium, or long wavelength, or short, intermediate, and long wavelength cones. So right, one set is good at seeing the blue-violet range, one green, and one yellow. But the middle and long range cones can cover the red end of the spectrum pretty well. So the number of colors that we can see is determined by the number of cone types that we have. And it's also true that other animals have different systems for this. So like dogs aren't completely colorblind, but they would only have two kinds of cones. So they can see a smaller number of combinations of colors than we can. So that's what the final slide is about. Then there are two more simulations I want to show off for a few minutes here before leaving you to explore them. Okay, so we normally have three kinds of cones and can distinguish millions of colors. I've linked to this article on Canvas. There are some people who are thought to have a mutation where they get an extra kind of perceptor, right? More often than not, it's in women, and I think I read that many of them would have like a colorblind father or something like this. But if you have an extra type of cone in there, you can see color combinations that we can't. And there are various other creatures. I think the mantis shrimp is one example, but there are other animals that instead of having two kinds of cones or three like us, they might have four and can see millions more, right? The rest of these are links that I've included in Canvas, but there are color phenomena like this picture here is the Bidwell's disk. Depending on which way this spins, you'll see either something red or something greenish, or what would be the opposite of that? Maybe cyan, depending on which way it turns. But I'm going to talk more about the eye and color saturation of the eye a little bit later. You can explore plenty of those links later on your own, so I'm not gonna dwell on it right here. What I do want to show are some useful things that you can explore for the homework. Let me do that. So we've already done some color mixing. We can also paint with CM and Y. So this is combining pigments, right? So this one, right? You're supposed to design the football uniform, and I might as well go advanced, right? We can, right, take cyan and say, give me fully cyan. But if you mix, if you combine cyan and magenta, you get blue. If you combine the full yellow pigment to that, then you get something completely black. So remember, like something that's cyan is reflecting you blue and green and absorbing the red. And the magenta is absorbing green, and yellow is absorbing blue. So if you absorb all three, you're going to get black. Now, if you go like part way, you might get a grayish color or something brown, something like this. So mixing pigments can happen in a bunch of different ways. You can get a light gray by absorbing a little bit of all of the colors, or we can get like green by going most of the way on these. Like if I turn the magenta filter off, then the green gets reflected, right? So that's one exploration you can do. I also want to show the stage lighting one, because this one, okay, this one uses principles of color absorption and color addition. So what we have are characters. So there's the black pan, the red apple, the green pear, the yellow banana, the blue berry. I guess that's a purple grape. The cyan cup of water, even though I want my water to be clear. I don't know, we're just gonna roll with it. Or the white egg. And so under white light, you see all of these characters as their natural color. But we can use the principle of absorption and color addition to figure out what they look under different colors. So for example, like a black object is something that will absorb any color of light that it gets. So even under white light, it absorbs everything and you get nothing back. So no matter what color light you put on it, it's going to look black. What's exciting is, or at least more exciting for me, is when I take something that's a different color and put different colors of light on it. So, right, yellow light is a combination of red and green, and a yellow object absorbs blue and reflects red and green. So if you're giving it red and green and it reflects red and green, it's going to look like it did before. But if you put a green light on this yellow banana, it will look green. Yellow bananas can reflect red and green, but I'm only giving it green. So that's all you get. Likewise, if you put a red light on it, it looks red. Likewise with a magenta light on it. So magenta is made of blue light and red light. The yellow banana will only give you the red light back, and it'll absorb the blue. So you'll see it as red. Right. Okay, some other, under blue light, the yellow banana looks black because the yellow banana absorbs blue and reflects red and green. Red and green make yellow. So if right, a yellow banana absorbs blue. So if you shine blue on it, it looks black. You look at one of the primary colors here, a blue thing. Yeah, let's do blue. So a blue thing reflects blue light. So if you give it blue light, it looks blue. Magenta is partly blue, so you get it back. Cyan is partly blue, so you get it back. Red has no blue in it. Green has no blue in it. So this blueberry will absorb those two colors and give you nothing back. Same with yellow. Yellow has no blue light as part of its mixture, so the blueberry will not give you anything back. Right. So those are definitely color mixings you can play with. All right. Just confirming to myself, I think I've gone through the slides, and a lot of this is just reading you can do and exploring you can do with those interactive links. So I'm gonna stop it there, and I think with this now I've got enough stuff for the first 2 weeks for when we come back, and I'll think more afterwards. Definitely want us to do those laser experiments that I alluded to earlier. So I'll think about how I give those and what more I want to do in the time we have left. I hope you're all safe and well, and I'll talk to you soon.